Hey, welcome to my Introduction to Mathematical Proofs playlist. Today we will learn a single word of Latin, contra. Contra means against or contrasting. That's contra, contrasting. And you might have seen a similar version of this, pro and cons, pros and contra. Pro means for. When you make a pro and cons list, it literally means for and against. So you make a list of why something is good and why something is bad. Okay, back to the topic of proofs. The reason we introduce implications is because they are a massive portion of the proofs you'll end up doing in the future. Either regular implication or double-sided implications, the if and only if, right? We want to find all the ways that we want to prove an implication. And there's two ways that we can prove implications other than the traditional path. Before we talk about that, I forgot to mention that last time. If we look at the truth table of double-sided implications, we use this weird symbol, the arrow pointing in both directions. So two lines in the middle and an arrow pointing in both directions. It's the same as, or logically equivalent to x implies y and y implies x. So they're actually the exact same thing. Now we're going to introduce a technique that we alluded to last time called the contrapositive. Consider the statement, if it is raining, then kids stay inside. There's only one time where we gain information, that being when it's raining. So when it's raining, we know for a fact that kids stay inside, according to the truth table. But what else do we gain this information? Imagine that this implication is true. Well, if the kids don't stay inside, by the truth table, because the implication is true, it can't be raining. If y is true, then x must be false for an implication to be true. That's the main idea for contrapositive. So pretty much, we're going to look at not y implies not x and see how the truth table for this works out. So we'll just slowly look through this. We have x, y, x implies y. Then we have not x and not y. And then we add in not y implies not x. And you'll notice they're logically equivalent. They're actually the exact same thing. It's actually very interesting. Now let's just look at a neat example. So let's just say for all x natural numbers, if x squared plus 1 is a prime, then x is even or x is equal to 1. So we can solve this directly, but I think I'll do contrapositive to explain why this works. So remember, we're going to use De Morgan's law. So we say that x is even or x is equal to 1. So not a or b is the same as not a and not b. So the actual contrapositive, what we're going to show is that if x is odd and x is greater than 1, remember x is a natural number and it's not equal to 1, so it must be greater than 1, then x squared plus 1 is not a prime or it's a composite number. So let's just write x as a odd number and we expand this out and then bam. And since x is greater than 1, x squared plus 1 is greater than 2, and since 2 is the only even prime, we must know for a fact that x squared plus 1 is composite. Here, both directions, as in directly and the contrapositive, both are actually effective. Both work perfectly fine, but it's just another technique to think about how you'd want to do it. Essentially, x implies y is the same as not y implies not x. They're equivalent, like how definitions are equivalent because they have the same truth table. So you can prove any implication either directly or by contrapositive. The question you might want to ask is, when do we want to work with contrapositives? When we're working with like maybe equalities or strict conditions, maybe sometimes what we want to show about y, so x implies y is like a very, very like loose condition. But the negation of that is a very strict condition, which is something that we might want to work with. And I really love contrapositive. It's really fun. And it doesn't always work, right? It doesn't always make the question easier. Usually they say about the same difficulty, but it's always good to have another tool. Now, if you follow along with the worksheets, you've probably seen this before. One of the most powerful tools that you'll have is called a contradiction. The idea is this. We have a proposition. We want to prove it, right? But what if we show that it just can't be true? As in, it's impossible for it to be true, because if it were true, it'd break our previous notions or preconceptions about what math is. It'll break the established set of rules we have. So we're going to assume that a result is false, and then through logical steps reach a conclusion that's clearly false. For example, maybe we'll get that x squared is less than 0. Clearly there's a mistake somewhere, and every step is valid up to this point, so our assumption must have been wrong. Since our assumption is wrong, the result must have been true the whole time. Let's just run through an example. Prove that there are infinitely many primes. Here's why it's so powerful. You can assume the exact opposite of what you want to show. We have more things to work with, more ways to approach a problem, but this freedom comes with a cost. We're going to talk about this later, but let's run through this proof. How would you prove something like this? And at first glance, you'd be like, okay, this doesn't really make sense. How do you show that there's an infinite amount of something? Well, this is where contradiction shines. It's not actually just for implications, but actually any result. A contradiction is very powerful because you can limit the scope, or once again, take the negation of something, which might be easier. So here, maybe let's just assume that there aren't infinitely many primes and see how we can break the laws of mathematics. So we're going to write out our list of finitely many primes. So P1 is the first prime, P2 is the second prime, and Pn is the final prime. So now the question is, okay, we have our list of primes. Where's our contradiction? Remember, we want to show that there are infinitely many primes. So maybe let's try to find a new prime number. Maybe that sounds like a good way to go. So let's write out this number n and have it be all the primes we've listed out so far multiplied. So P1 times P2 multiplied by all the way to Pn. Then every single prime divides n here. Now, what divides n plus 1? If any prime in our list were to divide n plus 1, it couldn't have divided n. If we add 1 to a number that was divisible by a prime, well, then the prime no longer divides it. Think about it. If something is divisible by a number greater than 2, adding 1 means that it isn't divisible anymore. You can't cleanly divide out the number. Since every number divides capital N, or n, no primes divide n plus 1. So it must be a new prime number by definition. And there's two ways that we can think about this. Either we can keep repeating this process and generate infinitely many primes. Well, then it kind of is like a contradiction, but then it's also just a direct proof. Or we recognize the fact that our assumption was incorrect. The fact that there are finitely many primes, the assumption we made was clearly wrong, since we just found one more. So there must be infinitely many primes. And here's where the double-edged sword, or where the problem with contradiction comes in. It's a very powerful tool, but if it's used incorrectly, like any other tool, it can prove wrong results about something. And sometimes when you do proofs with contradiction, what can happen is you make steps that don't actually make sense, that are kind of hard to catch, that you wouldn't make otherwise when you're proving it directly. So we arrive at a contradiction through broken jumps, not really sound steps. And here's the classic example of what a wrong proof is. Let a is equal to b, then multiply both sides by b. So you get ab is equal to b squared, then you get ab minus a squared is equal to b squared minus a squared. On the left side we factor out an a, on the right side we use difference of squares. Divide by b minus a, we get a is equal to b plus a. So 0 is equal to b. Or you can show that 0 is equal to a. But then like a could be literally any number. So it's just math. Is math fake here? What happened here? We didn't even assume a contradiction and we still broke the laws of mathematics. These are the types of steps that are going to happen whenever you're doing proof of the contradiction. And sometimes it'll just be like, what happened here? What did I do wrong? And here's where the issue is. B minus a is equal to 0 because a is equal to b. So we divide both sides by 0. That's illegal. That's illegal. And maybe you'll notice that when you do ab minus a squared is equal to b squared minus a squared, 0 is equal to 0. You're seeing that 0 is equal to 0 in more complicated terms. So when you divide by 0, you get some whack math magic happening. So before that, everything is logically sound, technically, because 0 is equal to 0. But then after that, when you divide by 0, you get some issues. That was a lot of logic. It's kind of annoying, not that fun to teach, not that fun to do, but it's something that you have to understand. Don't worry, we're going to tackle more interesting problems from this point onwards. And, I went through a lot of definitions and a lot of things that happened. A lot of this will just come through experience and time. So you can always tackle some of these problems on your own if you're ever feeling unsure or rewatch the videos. But until then, I will see you later. Bye.